Hey guys, welcome back to another episode, and we are going to continue with our complex numbers. Finally today we'll be taking a look at some of the different forms that complex numbers can be represented in. So previously you guys would have learned the basic form. Z is equal to x plus iy. All right, and let me just give you guys a visual representation of what that looks like again on the complex plane. If we were to set up our imaginary and our real axis here, all right, and let's just say we had the complex number x plus iy. If we're representing the complex number x plus iy, then that means that this is our x and this over here is our y, and we'll also put in theta to represent our angle. And because I said with all locations of complex numbers you can treat it as a radius, the distance from that origin to the actual point, we will also move on to call that r, which is the length of our complex number there. Alright guys, so, and this is a right angle triangle, and as with all rules in math, once you have a right angle triangle, trigonometry rules do apply. So looking at this triangle here, you can see that we can actually get values for, if we were to find sine theta, just remembering sine theta is opposite over hypotenuse, then you can clearly tell if I were to put my y in on this side instead. Okay, so just writing in my y over there, then sine theta being opposite over hypotenuse would give us y on r. Similarly, if we had to find a value for cos theta, which is adjacent over hypotenuse, we'll simply get x over r. Now, looking at those values means that if we were to make y and x the subject of the formula, that would imply, via rearrangement, that y has a value, of r sine theta, and x simply has a value of r cos theta. So we kind of have two little small substitutions that we can actually take, and we can substitute them into our standard form. Now, if we do that, here's what's going to happen. We will get z is equal to r cos theta plus I by r sine theta. And if we were to just do a bit of factorization, we would get a form that looks like this. R open bracket cos theta plus I sine theta. And because this has components of trig functions in it, it's said to be known as the trig form, and more frequently and more popularly heard in textbooks, you will hear people calling this the polar form. Alright, so sometimes you may have to transition between these two types of forms, and in order to transition, you just really essentially need to know the values of r and theta. Once you have those values, it's just a simple matter of substituting into your relevant formats, and you could go ahead and move very smoothly along. Let me show you how, by example, you can transition from that standard form here into our polar form. So hold on. All right. So for example, okay, let's look at a complex number z being equal to 3 plus I. And if we were to use our formulas, r is simply equal to the length of that complex number, which is given by the square root of x squared plus y squared. Okay, so that gives us the square root of 10. Now, similarly, we would have to find our angle theta. And our angle theta is given by the argument of c, which is equal to tan inverse of y on x. In this case, our value of y is 1, and our value of x is 3. Now, there's no exact value for that, so you would have to go to your calculator in radian mode and you should generate an answer of 0.322 correct to 3 significant figures there. All right, you may be asking yourself, well, that's what we usually do for the standard form. We find r and theta. Why do we need to do it for the polar form? Well, it's because of the form. If we would like to convert this complex number z is equal to 3 plus I in the polar form, z is equal to r, open brackets, cos theta plus I sine theta, then we would actually need to know this value and the values of theta. So therefore, transitioning this into our polar form, we are simply going to put everything together. So r, we got the value of r to be the square root of 10. So we're going to write it in first because that's how the form goes. We're following this. All right. Then we're going to open our bracket and say cos of, what was the angle we got? The angle we got was 0.322. So we're going to simply write it. You don't have to find the values in a calculator. You just need to write it in the form. So retaining that theta value, whatever it is, that would be your final answer. And this is what the polar form of a complex number looks like. And that's how you would convert a standard complex number in the form x plus iy to its polar form. Very, very simple and easy. And just take note, of course, the hardest part sometimes is when you have to find theta, you need to remember which quadrant does it lie, so that you either have to subtract or add pi depending on if it lies in quadrant 2 or 3. Okay guys, so let's move on to another form that complex numbers can take. Okay, so on screen you'll see the words exponential form. All right, so we're actually hitting up every single aspect of complex numbers in different varieties here. So I am actually for this video just simply going to state what the exponential form of a complex number looks like. It has r in it, and then of course because it's the exponential form it has that e, and it's raised to the power of I theta. So you will see that identifier I being present as the power and our value for the argument up top next to that I. All right, so this is the standard form. Now there is a proof for this, but it belongs to a certain expansion series that you guys will see when we're doing sequences and series, and we will come back to that proof in the future. But for now, the exponential form of a complex number looks like r e to the I theta. And by example, let me show you guys how. Am I getting tongue-tied? Let me show you guys by example how you would move from a typical form 1 plus I into the form z is equal to r e to the I theta. So one thing you could notice already easily happening is when you're moving from one form to the other, you actually always need to find that value of r and theta, your length, your modulus, and you always need to find the value of your argument as well. So with the modulus, you'll get 1 squared plus 1 squared, which is simply root 2. All right, and similarly, our argument of our complex number z is simply going to be equal to tan inverse of y on x. All right, and our y is 1, our x is 1, so that's tan inverse of 1, which gives you a perfect value of pi on 4 radians. All right, guys, so now that we have values for r and theta, therefore, in exponential form will simply look as follows. Z is equal to r, which is root 2, so we're putting it in this form here. Root 2 e, they say to the I theta. So theta has a value of pi on 4, and we can write the I in front, or we can write it at the end. Now, generally it's written after for the sake of looks. So even though it's I theta in the format, you will frequently see people just switch it up when it comes to the answers. They write the angle first and then the I. And guys, that's it. That's how you would move from the exponential form to the x plus iy form to back and forth. And you can actually move from polar form to exponential form to the x plus iy form in any ways they come. And I think you would see me doing a lot of those examples in the tutorial sessions that I have posted up since last year. So you guys, if you want some more detailed examples and workings and past papers and stuff like that, you guys can be sure to view those in those other videos. So this video is really just to kind of give you guys a small tiny nitty gritty into what exactly the exponential form looks like, and the polar form, and what they're essentially used to do. It's nothing too much. It's just a simple stepping stone from one to the other. All right, guys. So it was good to be with you for this very, very short video. And stay tuned just for like a couple more minutes, because I'm actually going to end the video with a bit of De Moivre's theorem. I think that it's necessary to introduce you guys to it while we're doing complex numbers, because a lot of students always ask for it, and then they have to wait till you reach module 2 when you're doing expansions and stuff like that. And then again, it comes in question 1. So I'd like to show you guys that up next. Okay, guys, so first up, you'll notice that the word De Moivre's theorem in and of itself is kind of a tricky word to spell. Okay, so that's what it looks like. And De Moivre's theorem was developed a long time ago by somebody who was playing around with the polar form of a complex number. So like, you know, we just did what the polar form of a complex number looks like. It's r cos theta plus I sine theta. And I guess over the period of time, they thought to themselves, hey, what if we just were to square? What if we were to square this? I wonder what would happen. So, of course, you know, if you square that, you get r squared by cos theta plus I sine theta all squared. And if you use your rules of shortcutting, squaring, when you have two terms in brackets, you get cos squared theta plus I squared sine squared theta plus 2 cos theta. Let me just shift this to the side here because we're going to be doing a bit of writing. 2 cos theta sine theta. Alright, guys, and you can immediately see here we have those double angle formulas coming to play. So you need to know your trig identities. Alright, and you're going to get r squared, open brackets, cos squared theta. Remember, this I squared represents -1. So you're going to get minus sine squared theta. And 2 cos theta sine theta, you guys should know at this stage, is simply double angle I sine. Oh, I forgot my I here. I sine 2 theta. Alright, and there's another identity as well. I just saw it. Cos squared theta minus sine squared theta can actually be cos 2 theta. So let's switch that up right here. Alright, so you have cos 2 theta. So by the use of double angle formulas, I will highlight what I used. Double angle identities, sorry. Alright, we have replaced this and this with the double angles, and we end up with something that looks like that in brackets. Now, according to the standard form, alright, according to the standard form, when it comes to polar numbers, well, polar complex numbers, you can see a little bit of a pattern happening here. If I were to write z squared right here, you'd see, well, hey, initially when z was raised to the power of 1, r was to the power of 1, and that angle in front was really just like theta. And suddenly, when you have the power of 2, you're seeing the r being raised to the power of 2, as well as there being a 2 in front of each of the angles. So that raised a level of curiosity, probably in whoever was doing this. I think his name was De Moivre. And he wanted to find out if the pattern is real, if he can make it into a theorem. So what he did is he went on to find z cubed. Now I'm not going to do that on screen. You guys can test it out. But interestingly enough, when he went on to find z cubed, it did in fact end up being z cubed open bracket cos 3 theta plus I sine 3 theta. So I guess a lot of testing went on and on and on and on to the point where eventually it became a theorem that says z raised to any power can be further expanded into r to that power cos of that power plus I sine of that same n theta being present there. And this result was extended into something that they now call De Moivre's theorem, where De Moivre's theorem states that, let me just go up one. All right, so here is it, the big one. So eventually, using all of these proofs and theorems that were found out after excessive discoveries, De Moivre's theorem just simply states for any real number that cos of n theta plus I sine of theta, raised to any power n produces n theta plus I sine n theta. Okay guys, and that essentially is what De Moivre's theorem is all about, showing you how for your polar form, if you have that complex number being raised to any power in particular, you can actually by extension just write that power in front of your theta value, and you can also raise it if there's an r present. You can raise it to that power as well. And that's as much as you would need to know for De Moivre's theorem. When we're doing questions and stuff, you'll see how it's applied. Actually, I think I may give you guys just an example to look at. Let me give you an example of how to apply De Moivre's theorem. Okay, so let's just say question, so example. Let's just say they wanted you to calculate or evaluate the value of cos of pi on 4 plus I sine of pi on 4 raised to a power of 8. Now this is a high power. Nobody in their right mind is going to multiply this in brackets 8 times. So what you can do is you can apply that De Moivre's theorem that says, well, hey, if there's a power up top, we know that we can actually just take that value and we can multiply by the existing angle, so that we can use De Moivre's theorem to simplify this into pi on 4 multiplied by that given power of 8. All right, and you can write it before or after, it doesn't really matter. You will end up getting cos of 2 pi plus I sine of 2 pi. And you guys know that sine of 2 pi will just go to 0. All right, I wanted to cross it out. That goes to 0, and you'd end up just getting cos of 2 pi, which has a value of 1. And that is how you can apply De Moivre's theorem. Now, a lot of times, you will have larger expansions with De Moivre's theorem where they want you to actually find an expression for cos of n theta and sine of n theta. For example, let me get into one of those while we're on the topic. Okay, so let's just scroll up here. I think I may have to like erase because I might need quite a bit of space. All right. Okay, so sometimes besides moving from one form to the other, they can ask you to use De Moivre's theorem. All right, they can ask you to use De Moivre's theorem to express values for like cos of an n theta value or sine of an n theta value. So let's look at the example where they use the Moivre's theorem to express cos of 5 theta being equal to something, and it has to be in terms of cos theta only. All right, so it's kind of like you want an identity, one expression for the value of cos 5 theta, but you want that to only be in terms of cos theta. Now, how do we use the Moivre's theorem to do this? Well, first of all, we have to remember what the Moivre's theorem looks like. All right, so the Moivre's theorem goes as follows. If you were given cos of n theta plus I sine of n theta, it's the same as cos of theta plus I sine of theta raised to that power of n. That is the Moivre's theorem right here, right? You have that polar form without the r present, and raising it to a power just means placing that power in front of your theta. All right, so using this knowledge, one possible way of using the Moivre's theorem to find a value for just cos theta alone is to actually use the entire of the Moivre's theorem. And because we're dealing with real and imaginary parts, what happens is we end up equating real or imaginary parts based on what is required in the question. So let's look at this question. Over here we have cos 5 theta. So for this question, we're going to consider n, all right, having a value of 5. And if n has a value of 5 in this question, that means that our de Moivre's theorem is going to look as follows. All right, you'll have sine 5 theta on one side is equal to cos theta plus I sine theta all to the power of 5. All right, and of course we have an equation here. We have a left-hand side and we have a right-hand side to an equation. So because the question is asking for cos 5 theta, what we will be doing at the end is we will be equating, this is the real part, right? This is the imaginary part because of that identifier. We'll be equating the real parts of the left-hand side with the real parts of the right-hand side. But you see, on the right-hand side, we do not essentially have an expansion. We would have to multiply that by itself 5 times. But there's actually a way to do this expansion, and we do it using Pascal's triangle, if you guys can remember that from Form 6, Lower 6. So let's do that right now. Let me show you guys how you would expand that right-hand side. All right, so taking this up just a little bit. All right. Okay, so to expand that, we're going to have to get into a little bit of Pascal's triangle. If you guys can remember how to build a Pascal's triangle. When you have something raised to a certain power, you can use Pascal's triangle to figure out each of the coefficients in front of each term. So you start a Pascal's triangle with 1 and 2 ones on either side. And essentially what you keep doing is adding the numbers that are next to each other, and then you keep introducing ones at the ends. So 1 plus 1 gives us 2, and then we will introduce 2 ones at the end. 1 plus 2 gives us 3 here, and we add 2 ones to the end. And how do we know when to stop? Well, we have to observe the power given in the question. In this case, it's 5. So if we're dealing with something that had a power of 0, we would only need the first line. A power of 1, a power of 2, a power of 3, and so on. So that means for this question, we need 2 more lines. All right, so we're going to add that over here. And then one final line. We're going to get 10, 10, 5, 1, 5, 1. So this line is what we're going to use to tell us, first of all, how many terms we're going to get in the expansion of this right-hand side here. We're going to get 1, 2, 3, 4, 5, 6 terms, and the coefficient in front of each term is going to be each of these numbers as follows. So let's go ahead and let's expand that right-hand side using that knowledge of Pascal's triangle. So expanding the right-hand side will give us the first term in bracket is cos theta. So we'll write down that first term to the highest power present, which is 5. All right. And of course, the coefficient in front of that is going to be 1. So we won't write it in. And then the I sine theta will have to be raised to the power of 0 such that the sum of these two powers should always be equal to the power given in the question. So anything raised to the power of 0 gives us 1. So this actually disappears into 1. So that first term is going to give us cos to the power of 5 theta. And then we continue. Second term, we're going to place the 5 in front. Then we're going to use the first term and we're going to reduce the power by 1. So pretty much you start with your first term and you start from the highest power and you keep reducing. So you start from the highest power and you keep reducing it. And for the second term, you start from the lowest power and you keep increasing the power. All right. Take note that for each term, you must make sure that the powers for both terms add up to 5 always. So for example, now we will have I sine theta present. And in order for this power to add up to 5, the two powers to add up to 5, the power above I sine theta should be 1 because 4 plus 1 gives us 5. And we do not need to input that there because obviously that's understood. And you keep doing this all the way till you reach the end. All right, so you guys can try that on your own. I'll just tell you what the last term is going to look like. The last term will actually always only be the last value inside that bracket there, raised to that highest power. So we will have I being raised to the power of 5, as well as that sine being raised to the power of 5 there. And when you expand this, all right, what you want to do is you want to only highlight, for this question, the real parts. And the reason for that is because initially, if you look at the question wants an expression for cos 5 theta. And cos 5 theta is a real part. Remember over here, cos 5 theta is the real part. So essentially what you want to do is you want to equate your real parts of both your left-hand side and your right-hand side. So over here, I'll call this our essential equation. This is what we're looking at. So looking at equation 1 on the left, if we were to equate our real parts, you will get that cos 5 theta that you're looking for. And on the right-hand side, after expanding it in blue, all the components of the real part end up being cos to the 5 theta plus, actually it turned out to be minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the power of 4 theta. So it's a lot of algebra. It's not hard. It's pretty easy. It's just a lot of algebra. And one thing you really need to be strong on when you're doing these questions involving De Moivre's theorem is that you really need to know your trig identities. Because remember, the question wants the answer only in terms of cos theta, and you can see the presence of sine squared theta and sine squared theta all squared again, right? So you need to use the identity sine squared theta being equal to 1 minus cos squared theta in order to get rid of these two chunky parts over here. And after using that identity, you should be able to end up getting 16 cos 5 theta minus 20 cos cubed theta plus 5 cos theta. All right, so that is how you would actually apply De Moivre's theorem to find an identity or value for stuff like cos 5 theta, sine 5 theta. If we had to find the value for sine 5 theta, we would have simply had to equate the imaginary parts on both sides instead. You can do it for sine of 3 theta. It really it could be applied to any power, right? And it tends to be a lengthy bit of working. Now, these sessions here, these videos are not tutorial videos. They are meant to introduce and teach the core essence of the topic. If you would like to see tutorial sessions on this topic, then sit through my videos. I think I do have a tutorial, De Moivre's theorem tutorial, where I did questions and stuff like that in detail without skipping any steps in between and so on. So today, what did we learn? You guys learned that besides the forms equals x plus iy, there's also some other forms you can express complex numbers, such as the polar form, aka trigonometric form, the exponential form. You can move back and forth between terms. You also learned that you can use De Moivre's theorem to find exact values for like angles that have an nth degree, like cos n theta. And you can also, furthermore, you can use De Moivre's theorem to evaluate expressions of the form cos n theta plus I sin n theta raised to a power. Okay, so very, very useful things you can do with De Moivre's theorem and moving from one form back and forth. Okay, guys, so I hope that you guys got the general essence of what complex numbers are all about. This is the end and last session we will be doing on it, and we will be moving forward on to another topic. Please watch the tutorial sessions where you will see a mix of past papers on all different types of questions that could come within complex numbers. So it was good to be with you guys. Take care. See you guys next session. Bye.